So, in my last lecture, I have introduced the course MEMS and Microsystems. So, by now you know that in MEMS and Microsystems, one of the important block is a sensor block. And today's lecture, I will highlight the sensor and I will introduce sensor, then we will go to the microsensor and different aspects of sensor, its specification required and its technological aspects. All these things I will discuss in today's lecture. And sensor is a very important device, and now with in microsystem we use microsensors, and I will discuss what is microsensor. And in particular in MEMS or microsystem we normally use semiconductor sensors. And again, why semiconductor sensors? Because semiconductor materials are used in many ICs and VLSI. So, if I can make the sensor out of the semiconductor material, then it will be easy for us to integrate both the sensor part and circuit part together, and that is why a lot of sensors are coming out making use of semiconductor materials. And in the first, let us see what sensor means. And sensor basically is a word, is a coming from a Latin word sentire, and that means to perceive. That is derived from Latin word sentire, and lot of definitions are given for sensors. Basically, it gives information about the physical and chemical signals which could not otherwise be directly perceived by our senses. And some people define sensor is a device that responds to a physical or chemical some stimulus and is transmit a resulting impulse as for measurement. That means some physical thing which cannot be measured, it has to be converted into some measurable quantity. Then only we will understand how the sensor is behaving and how the sensor is sensing. Until and unless we detect and measure the output, then there is no meaning of that particular sensor. It detects an input signal, that signal obviously in some form energy, and it converts it to an appropriate output signal which can be measured and which is taken as output. That is the main job of sensor. Now, the microsensor and semiconductor sensors, we are dealing with microsensors which are based on semiconductor material mostly. They are small size in low cost, that is one advantage. They use fabrication processes of integrated circuits or VLSI, that is a very good advantage. And another thing, if the as like ICs, the semiconductor sensors can be batch fabricated, and batch processing improves performance as well as cost ratio, and that is why people are now giving lot of importance on semiconductor sensors. And at the end it integrates with microelectronic circuit, as I mentioned few minutes back. That is why this is coming up in a big way, and this particular sensor is called integrated microsensors, or sometimes it is called smart sensors. Now, the another block which is always sometimes known as the transducer, and sometimes some people confuse between transducer and sensor. Basically, both sensor and transducers are synonymous forms, and transducer word is again derived from another Latin word which is known as transducere, and that means to lead across, a device that converts energy from some system to another in the same or in different form. So, you see, transducer normally transfer the energy from one form to the same form or in another form. That means, if the sound, if we apply the input energy as a sound energy, then transducer output will also be sound energy, then it is called sound energy of this different magnitude. So, that we do not call it sensor. For example, amplifier device, its input signal is the electrical signal and its output signal is also electrical signal. So, then the same form of energy is obtained at the output, but with a different magnitude. So, that amplifier is not called a sensor, but on the other hand a microphone is called a sensor, because there at the input energy is sound energy or acoustic energy and output energy is electrical energy. That means the input and output energy are not same, they are different. So, here is the little bit difference between a sensor and transducer. That means on the other hand we can say all the transducers are sensors, okay, and sensors are, sorry, all the sensors are transducers, but all transducers are not sensors, isn't it? So, just like if you compare the example of the microphone and also the amplifier, then it is clear, okay. And then a information processing system where sensors are used. So, in an information processing system there are three blocks and they are known as sensor, processor and transducer or actuator, sorry, sensor, processor and actuator. So, input signal, which is the measurand quantity, so that is coming to the sensor and that is input transducer, and then this sensor converts the input signal into another form which can be given to processor, and that form of energy is to be processed by the processor, okay. So, that means normally processor deals with electrical energy. So, the sensor must then convert non-electrical energy into the electrical energy, okay. So, that in the next block, which is the processor block, and that block can process that output of the sensor signal, and the other block after processor is actuator. So, actuator is a device that converts an electrical signal into non-electrical signal. For example, if the acoustic energy is transmitted in a PA system, then at the end of it you have to get back the acoustic energy. So, in between you can process the acoustic signal by different blocks, and those building blocks are electronic blocks like amplifier, like mixer, like filters. Those are there to get back the original energy, that is say acoustic energy, into a again acoustic energy, but in amplified fashion or free of noise, etc. So, then the actuator means always it is at the output side of the information processing system and it gives the output signal, and that output signal is perceived by the people, that means sensed by the people, and from there they will understand the quality of the input energy, okay. So, now these blocks, sensor, processor and actuator together they form information processing system, or sometimes it is also known as a microsystem. Now, the microsensors, if you look into the building block of microsensor, then we can say here you see sensor, input and output, there are two parts. Here you can see the E is a energy, one form of energy, E bar is another form of energy, and E bar represents the electrical quantity and E bar represents the non-electrical quantity and E represents the electrical quantity. So, the sensor basically converts the non-electrical quantity into its electrical quantity. Then another block is actuator. The actuator input is electrical again and output may be non-electrical. Non-electrical means it may be mechanical energy, it may be acoustical energy, it may be optical energy, it may be magnetic energy. So, but input is electrical, that is the actuator block, and the other one C here is the processor block. There you can see the input is also electrical and output is also electrical. So, a processor changes input which is electrical form to output which is also electrical form, but maybe the amplitude or may be frequency changed at the output. okay, depending on the block which you are going to use it. So, these are the 3 blocks which transform some quantity of energy into other form of energy. Now, again, what are the different forms of energy the sensors and actuator deals? They are mainly the electrical, thermal, radiation, mechanical, magnetic and biochemical energy. Now, the electrical here is denoted by the word E, thermal is a T and R is a radiant energy, M is a mechanical energy, M is magnetic energy and C is biochemical energy. So, all this energy is at input and they transformed into electrical energy, that is the job of the sensor. Now, on the other hand, here vectorial representation of actuators is shown in the figure B. So, here the actuator gets electrical energy, then it converts it into either chemical energy or you see magnetic energy or mechanical energy or radiation energy or thermal energy. This is the vectorial representation of sensors and actuators. Now, the actuator system is shown in this particular diagram. So, in the actuator system, the actuation means it will act something, some either mechanical or some motion or movement or some color change or light intensity change, something will happen there. So, for that the whole system is again can be subdivided by different blocks. For example, first block is an amplifier where the input is also electrical energy and output is electrical energy. If I is the input, so output you are getting A star I. A is the amplification or gain. Okay. So, now this is fed into another block which S star 1 is basically electrical quantity. So, the electrical quantity is getting, but output it is getting magnetic energy. So, electrical to magnetic it changes. Now, this magnetic energy is fed, that is B is the magnetic flux. So, that is fed into another block which it takes with the magnetic energy, but its output is the mechanical energy, vibration or motion or displacement, whatever it is. That means from electrical to basically the mechanical motion, displacement or vibration, that conversion sometimes it needs another block which changes from electrical to magnetic energy. In some cases there are certain material which directly from electrical can be converted into mechanical vibration and motion, those you know is a piezoelectric material. So, input if you apply the electrical energy, electrical field, and output you will get the mechanical motion and vibration in this sort of crystals, but not always. If you do not use piezoelectric crystal, then you have to use some intermediate block which can convert into a magnetic, and then magnetic energy can easily convert it into vibration or displacement, something like that. So, that is the block diagram representation of the transduction processes within a magnetic actuator. Now, what are the different forms of energy converted by sensor? Those forms of energy are many. One is atomic energy, electrical energy, gravitational energy, magnetic energy and so on. So, atomic energy relates the force between nuclei and electrons. So, that is the atomic energy. Electrical energy pertains to electrical field, current or voltage. Gravitational energy, it is related to the gravitational attraction between a mass and the earth. Similarly, magnetic energy deals with magnetic field. So, other forms of energy are mass energy, mechanical energy, molecular energy and nuclear energy. So, mass energy is described by described by Einstein, and you know if mass is m, so energy equivalent of m is mc square, where c is the velocity of light. This is a famous Einstein equation, E equal to mc square. And mechanical energy pertains basically to the motion, displacement and force. So, those are mechanical energy. Molecular energy is basically the binding energy between the molecules is known as the molecular energy. So, nuclear energy is the binding energy between two nuclei. So, you can get the distinction between molecular energy and the nuclear energy. So, molecule to molecule, that binding energy is molecular energy, and nucleus to nucleus, that binding energy is called nuclear energy. Okay? And atomic energy is electrons with the nucleus. So, those three energies, little bit slight difference, all are related to the molecule structures, means atoms, nucleus or molecules. Okay? Now, other forms are also there, radiant energy and thermal energy. Radiant energy related to the electromagnetic radio waves, microwaves, infrared, visible light, ultraviolet, X-rays and gamma rays. Those are radiant energy. Many of these energies are available in space. So, some sensors are required, detector of infrared detectors or nuclear radiation, how much is coming from the space. So, we have to know what are the different forms of radiation available in space. Accordingly, utilizing the physical property of the materials, we can design the sensor. And the last form which is shown here is the thermal energy. Thermal energy related basically to kinetic energy of atoms and molecules. You know, the kinetic energy increases means kinetic energy increases means the temperature of that body also increases. So, it is directly related to the kinetic energy. Thermal energy is related to the kinetic energy, and and with the absorption of the radiation or absorption of light, the kinetic energy may increase, and as a result of its reflection is temperature of that body increases. So, these are the different forms of energy we come across, and accordingly we have to make sensors depending on or based on the properties of different materials. Now, what are the different types of signals we deal? Each form of energy has a corresponding signal associated with it, and those are chemical signal, that is basically atomic and molecular energy, electrical signal, magnetic signal, mechanical signal, which are gravitational and mechanical, radiant signal, thermal signal. So, these are different signals we are getting, and those signals is fed into your sensor system. Now, what are the measurands, that is the input signal to the sensor? The measurands are acoustic, level of the acoustic energy you want to measure sometimes, and what do you mean, what basically parameter of the acoustic energy you are going to measure? Those parameters are many. Those are basically wave amplitude of the acoustic signal, phase of the acoustic signal, polarization, spectrum and wave velocity. These are the various parameters of the acoustic signal. Any of the parameters you can measure in your sensor. You can measure the amplitude, you can measure the phase, you can measure the change of polarization of that particular signal, or you can change the wave velocity or the frequency change, which is basically coming from the frequency spectrum. Now, another form is biological measurements, and what is the biological measurements? That is basically the biomass. Biomass means what is this? That is its identities, that is in a biological material, what are the different components there, that is its identities. Then concentrations, for example, in a biological, say blood, lot of constituents are there, how much is your fat or cholesterol, that is the identity, how much is the creatinine, that is an identity, how much is your sugar, that is another identity, what is your urea, those are basically the biomass identities. Then concentration means what is the level of that particular identity, that means in a 1 milligram how much is that particular amount, or what is the concentration of that particular chemicals into your in the biomass, that is the concentration, and in what state it is lying there, in the biological body. So those are the three things which we have to measure, either all of them or any one of them. So that accordingly your sensor is to be designed. Then third one is a chemical. Chemical, again the components like the biological, that is identities, concentration and state. That means the identities means whether is a alkaline in chemical, whether it is alkaline or is acidic. So if it is alkaline, how much it is alkaline? If it is acidic, how much it is acidic? So those are the concentration, or in a particular chemical solution, what is the concentration of the solution? It is a, for example, KOH solution, which is frequently used in MEMS and micromachining MEMS laboratory. And how much percentage of KOH you are taking? That is not the composition of individual identity. That means the water and that particular the material, in what ratio it is mixed into the solution, and which state this particular chemical is lying. So all those things is to be known before we are going to use those particular chemical in either the sensing or actuation or in any processing side. So other is a radiation, and radiation means which type of radiation and its energy and intensity. Type of radiation means whether it is a alpha ray or beta ray or gamma ray, or it is ultraviolet ray, isn't it, or it is infrared ray. These are radiation, that is type. Energy and intensity, that means how strong is the radiation, and that is the intensity you are getting. Then from that particular intensity, how much energy you can get it. So the energy is and intensity are different. For the same intensity, the energy may be different. Okay. So that's why the type, energy, intensity, these are the different components of any radiant signal or radiant energy. Okay. Now the another one is electric. So electric means there are a lot of measurements in electrical energy. What are those measurements? Those measurements are charge, current, potential, potential difference, electric field means its amplitude, phase, polarization, spectrum. Spectrum means here frequency is also there in spectrum. Then conductivity, permittivity. Those are the different measurements in an electrical signal. Your sensor can measure or can identify the charge. Your sensor can measure the current. Your sensor can measure the frequency change of that particular electrical signal, or it can measure the conductivity or permittivity. So these are the different measurements, and all are electrical, all belong to the electrical signal, but measurements are different. And another one is a mechanical energy or mechanical signal. It has got enormous number of the measurements, like position means, what do you mean by position? Position means it is a linear movement or angular. The both are there, both called as a position. Then velocity, acceleration, force, stress or pressure, strain, mass or density, moment, torque, speed of flow, rate of mass transport, shape, roughness, orientation, stiffness, compliance, viscosity, crystallinity, structural integrity. So all these are the measurements. Okay. So those all belong to the mechanical signal or mechanical energy, all are. Now magnetic, what are the measurements? Those are the magnetic field means again coming the amplitude, phase, polarization and spectrum, magnetic flux and permeability. Next one is optical. What are the measurements in optical signal? Wave amplitude, phase, polarization, spectrum, wave velocity. Those are the various kinds of optical signal, and many of the optical sensors they show the change of polarization. Many of the optical signal they show the change of frequency, optical sensor and many of the optical sensor they show the optical intensity. So there are certain optical sensors are available when the intensity of the input signal is beyond a certain limit, then some actuation will be done, some switch is on, and if it is below that level, the switch is off. That is one kind of, that it depends on the intensity. Another is a optical signal, as soon as incident on particular sensor, then what will happen? It will say photo detector. So optical signal is there, and at the output you can get some electrical signal. That electrical signal can be used for some other controlling or some other actuation. So these are basically the input is optical, but what you are using there, that is optical amplitude. Whatever the amplitude is falling there, it works. Okay. And phase also is also used sometimes. Thermal and thermal energy measurements are temperature, flux, specific heat, thermal conductivity. These are all belong to the thermal energy. Now the technological aspects of the sensor is very important, and there are a lot of parameters which specify a particular sensor, and these parameters basically qualify a sensor whether it is good or bad. That means when you will choose a sensor for your particular application, you have to find certain parameters and you have to judge from that parameters whether that particular sensor serve your purpose or not. So those parameters, how these are controlled, how those parameters are defined, and how those parameters are achieved in fabrication, those things has to be kept in mind when you are going to design a sensor and or when you are going to use a sensor. And one such parameter is full scale input, another is full scale output, and another parameter is offset, linearity, and stability, hysteresis. These are the different parameters one is to look into before selection of a sensor. Now let us discuss little bit on full scale input or span, and here is basically the dynamic range over which a stimulus can be converted by a sensor. For broad span, it is expressed in decibels. That means full scale input means what is the range of the input which the sensor can sense, or output you can get it. That is the full scale input, or it is known as the span, and normally it is expressed in decibels. If for power ratio, you know the definition, 1 dB is 10 log P2 by P1. For voltage ratios, 1 dB is 20 log V2 by V1. For example, if the power ratio is a 10, so obviously decibel it will be 10 dB, and is a power ratio is 10 to the power 8, so the decibel it is 80 dB. So that it comes from this relation. If the voltage ratio is 10, so the decibel it will be 20 log V2 by V1, that is 20 dB. Okay. This is the normal unit by which the full scale input is expressed. Now the second technological aspects of sensor is full scale output. That is basically the algebraic difference between the endpoints of the output. That is the full scale output. Okay. And output format also you have to see. What is that? That is usually an electrical quantity and is a function of measurand. That means whether the output format is in voltage, it may be in voltage amplitude, change of capacitance, frequency output, or frequency modulated output. So these are different output formats you can get it from a sensor, and the full scale is the minimum to maximum output you can get, that is the total full scale, and that is also a parameter which you have to look when you are selecting a certain sensor for certain application. Now the other one is accuracy. How accurately a sensor can measure the input measurand. Basically it is inaccuracy. Although we are calling it the accuracy of sensor, it is basically the highest deviation of a value represented by the sensor from the ideal or true value. An example is given here. For example, you are going to measure the linear displacement, and ideal transfer is 1 millivolt 1 millimeter. For example, for 1 millivolt if you apply, the displacement is say 1 millimeter. That is the ideal transfer. Application of 1 millivolt, the displacement is 1 millimeter. Now if you apply in a certain sensor the input voltage is 10 volt and your observed displacement in 10.5 millimeter. So, in that case, what is the difference between the observed and ideally you should get 10 volt means you should get 10.5, but 10.5 minus 10 is a 0.5 millimeter is the deviation. So, 0.5 millimeter in 10 millimeter, so that means it is 5%. So, inaccuracy is here 5%. So, now inaccuracy is expressed as 5% or 0.5 millimeter. That is basically how the inaccuracy or its other word it is accuracy is defined, okay, in percentage. So, now the other one parameter is a calibration error. So, calibration error is basically the inaccuracy permitted by a manufacturer when sensor is calibrated at the factory. You look from this curve where the real line is here, which is basically given by a by the supplier from the factory. Now, here if you calibrate it with some known signal at your laboratory, you are getting this line. So, obviously it deviates from the real line. So, from the real line to your measured at the laboratory, so that is the calibration error. So, whatever calibration has been made at the manufacturer site, that is not same when you are going to measure it. Why? Because during the transportation or during the packaging or during the aging, so that calibration error may change, calibration line may change, and that means it is not highly stable. So, that means when you see the calibration curve at your laboratory, it deviates from your original which has been made at the manufacturer site maybe a long time back. So, that is the calibration error that you have to measure before you put the sensor in your system. And let us now see what are the other parameters which you look, that is hysteresis. Hysteresis is another important parameter. So, hysteresis, the word is familiar when you have studied the magnetism, magnetic hysteresis, you know it. Similarly, the hysteresis is also there in any form of energy, in any form of sensor. That means when you go on measuring the measurand by a sensor, and if you go on increasing the input measurand, so you are getting the output in a increasing way. Now, you come to a limit, what is the maximum limit you got it, then you decrease the measurand and see the output, and you will find the curve will not follow the same path. When increasing mode and when you are coming in the decreasing mode, it different path follows. If you plot the input and output curve, the difference of path gives the measure of the hysteresis. And here if you look into the picture, then you see here this is the curve which follows if you go on increasing the stimulus from low value to a high value. Similarly, if you from high value, from full scale is here, this is Fs means full scale point. If from the full scale point, if you reduce it the stimulus, then it follows a different path. Now, if you take the difference for the same stimulus, you see the same stimulus is here. Here is the point x and here is the point y. Difference between the x and y, which is h, and is the hysteresis. Okay. So, this hysteresis for an ideal sensor is not desired. Here I may mention that this hysteresis is a property of material. Different material has got different hysteresis property. For example, silicon has got minimum hysteresis. That is why silicon is one of the chosen material for sensor. For magnetic materials, so manganese, so iron or nickel, there this hysteresis quantity is more. So, you have to take care of that problem, because always a sensor does not work, the stimulus will increasing always. Sometimes you have to measure when stimulus, input stimulus is decreasing also, then is already the sensor is some other higher state. So, then it will not give you the actual reflection of the input stimulus. So, that is why it is very, very important. The other parameter which you have to take care is the resolution. So, resolution is the minimum change of the measurand value necessary to produce a detectable change in the output or smallest increments of stimulus that can be sensed. That is the resolution. What is the minimum amount of input signal which can give you a detectable output at the desired energy level which you are looking for. Okay. So, that is the resolution. So, resolution for analog and for digital sensors are different. Obviously, for analog sensor, this resolution is expressed in terms of units of the stimulus. For example, in a thermal resolution may be 0.5 degree centigrade or 1 degree centigrade or maybe 0.2 degree centigrade. In case of the electrical, it may be resolution say few microvolts or few millivolt like that. But if you look into the digital sensor, then the resolution is expressed in number of bits in data watt. For example, say 8 bits or 10 bits like that. So, that is the resolution in case of digital sensor. Now, the change in sensor performance within hours or days is also there, because performance may change, which is known as a drift. So, today you measure certain input stimulus using your sensor. If you measure the same input stimulus tomorrow or 1 month later, 1 year later, same sensor can give different output. That means that sensor has got drift, its property has changed. Also the aging, that means it depends on aging. So, this aging depends on what? Why after aging, after long time the performance is changed? It depends on various parameters. One is the storage condition and another is isolating material. What is isolating material? Means after fabrication of the sensor, if you cover the sensor with if you cover means if you coat or if you put a passivation layer, and if the passivation layer if you put a glass or if you put an epoxy, then you will find the aging effect will be different, because you see with aging your sensor material is coming across the environment, and environment has got lot of gases and chemical vapors, and with those gas and chemical vapor the reaction will take place with sensor materials and its property may change. But if you passivate it with proper material, so that it isolates, what isolates? The sensor materials and device will isolate from the environmental hazards, then the drifting may not take place. So, that means one of the cause of drifting is how you are isolating the device, and another is the storage condition. And there are certain sensors which are highly sensitive to humidity, some sensors are highly sensitive to temperature. Then you have to follow the storage condition, and in some cases the sensors will perform best at certain humidity level and certain temperature level. You have to preserve the sensor in that level. If you do not follow that, obviously the drifting will take place, you cannot prevent it. And so obviously what are the remedy for drift? There are few remedies. One, sensors need to be stimulated during design phase, need to be simulated, not stimulated, the sensor need to be simulated during design phase. That means there by simulation, what are the changes can take place, say little bit temperature rise or little bit humidity rise, that you can stimulate. What are the effects of change of temperature on various parameters, what is the effect of increase of the humidity on various parameters. From there you can stimulate you can simulate its properties, output properties, and then you can at your design phase you can change something so that drifting will be less. And if long term drift occurs, then some corrective action is needed. That means you have to calibrate the sensor time to time. Okay. So, these are the remedies for drift. Next one is the temperature. Many sensors change their behavior as temperature changes, because many of the materials which are used in sensors, their properties are dependent on temperature. That is why the complete the output performance of the sensor changes with the temperature of operation. Another is the self heating. So, some of the sensor will work if you apply some electrical power. So, if you apply electrical power to the sensor, automatically some current will flow from through different components of that particular sensor. So, a self heating is there. So, because of the self heating, the parameter property may change also. So, that is these are the causes which changes the sensor performance. Sensor accuracy usually specified for a given temperature range. For example, for 0 to 100 degree centigrade temperature range, so it may plus minus 2% variation may be there. Similarly, minus 30 to 0 degree plus minus 3% variation is there. So, that is mentioned when a manufacturer is marketing a particular sensor, what is the temperature variation of those sensors. Here this example is given to inform you that the temperature variation or the performance of the performance change of the sensor is not same in different temperature range. Some sensors are highly sensitive at very low temperature, fluctuation is more. Some are highly sensitive or its property changes drastically at very high temperature. So, the temperature variation or temperature drifting or thermal drift may vary in different temperature range, and that is mentioned in the manufacturer's the data sheet of any sensor. Now, the other is the reliability. So, when you are picking up a sensor for certain application, you must look for the reliability, how reliable it is. Okay. So, that means it will show you the ability to perform a required function under the stated conditions for a stated period. So, conditions are known and how do the sensor perform. So, that is the reliability. Okay. Same conditions, if it gives you different performance on different dates or different situation, then it is not reliable. Okay. Specified as a probability, the device will function without failure over a specified time or number of uses. That means reliability with respect to time, reliability with respect to use. That means the reliability with respect to use means frequent use if you make, and after that if you see if the same input is not giving the same output, that means not it is a time failure, because with time reliability is lost. Another is a, because it is related, specified time and specified use. In some sensor, even not used, if you keep it for a long time, you find its reliability also goes down. That is also you can say as the aging effect. Okay. So, reliability is affected by what parameters? Is affected by high temperature, is affected by high level of humidity, it is affected by mechanical shock, vibration, it is also affected by storage condition, thermal shock and temperature cycling. So, these are the different parameters which affect the reliability of a particular sensor. Now, the other technological aspects of sensors, those are ambient conditions allowed. That means, what are ambient conditions? Temperature, vibration, pressure, shock, moisture, electromagnetic field. That is one important parameter. The electromagnetic field is coming nowadays because of the application of lot of wireless devices. So, lot of electromagnetic fluctuations are there in your surroundings. So, that means that is coming as an ambient condition. In addition to that, moisture is also, we know, electromagnetic in addition to electromagnetic field, moisture, shock, vibration, sound level, sound pollution, those are the ambient condition. Whether those parameters affect your sensors or not, that you have to see. Another is the linearity, closeness between the calibration curve and a specified state line, that is the linearity. Okay. How close your calibration curve with a state line, that is your linearity. Some sensor shows the linear performance, some sensor does not show the linear performance. Okay. So, that you have to know from their physical principle and property, which sensor behaves linear, which does not behave linear, okay, and which is behaving linear, then how much is a drifting from the linear, that also is a parameter of a particular sensor. Then warm up time. Warm up time means, as I told you, that some sensors works when we apply certain electrical signal or power at the input. So after switching on, how much time it is taking to show the or to sense the input stimulus or to change the output with respect to the input, that is known as the warm up time. How much time it is taking for full functioning, okay. So that means time between applying sensor power and the moment when the sensor can operate within its sensing accuracy, that is known as the warm up time. So it's important sensing accuracy. As soon as you switch on, you may say some sensor you are getting output, but output is fluctuating, it's not stable, that we cannot consider, but it has to be stable and within the accuracy limit which has been specified by the manufacturer, it has come to that level, then we call it is okay, then that time we count as a warm up time. And another one is a saturation. At some levels of the input stimulus, the output signal of a sensor will no longer be responsive and the sensor is said to be saturated. If you go on the input stimulus, so output is increasing, but after certain limit the output may not increase, that is the saturation level it has reached. So normal definition of the saturation, that is also a technological parameter of a sensor. Now other technological aspects of the sensors are offset, that is output of a sensor with zero measurand applied at room temperature condition. Normally what we need, the offset is not a desired thing, but in some cases as soon as you switch on the supply of a sensor, you will get the output signal in spite of absence of the input signal. So a photodetector output is a voltage. So as soon as light is incident on a photodetector, you should get the output voltage or current. Photodetector normally current is the output stimulus, output measurement. So now if you don't switch on the light, even then if you get some current, then it is offset, and in that case it is known as, in case of photodetector, it is known as a dark current, we know it. Similarly in many of the sensor will have that property, and that should be as minimum as possible. When you make the calibration curve, if you package the total complete sensor, then you have to see whether you are reducing the offset to a minimum value or not. So that is another one of the important aspect of sensor when you are choosing it. Next is operating life. Minimum length of time over which the sensor will operate without changing performance characteristics beyond specified tolerance, because every sensor will have certain tolerance limit. So whether your output exceeds that tolerance limit or not, that you have to see. If the sensors gives you the output within that tolerance limit, so that till then you use the sensor. If it exceeds you that limit, you throw it. So that is the operating life of the sensor. Next is the overload characteristics. So overload characteristics, what does it mean? The maximum magnitude of a measurand that can be applied to a sensor without causing a change in performance beyond specified tolerance. Okay. So here is a beyond specified tolerance. It should maximum input or maximum magnitude of the measurand or stimulus, it can sense properly. That is the overload characteristics. So overloaded means you have given, if some sensor can, for example, say a acoustic sensor is measuring the output noise level, output sound level. So the sensor maximum can measure say 100 dB noise, 100 dB sound amplitude or whatever it is. So now if it is a sound level is so loud, is a 200 dB, so it's overloaded, so output is unreliable. It may show the exact value of the 200 dB or it may not. Okay, then that is not reliable. That means it has exceeded your specified the tolerance limit, so it behave erratic. So that's why that is basically overload characteristics is to be known for a particular sensor, so that you can uh, uh, use reliably up to that level. Okay, that is the overload characteristics. Then comes selectivity, sensitivity, and speed of response. Selectivity is again an important parameter. Why? Because I am giving you one example, and that example is again I am talking about the thermal sensor. So you are going to measure the temperature of a particular body. That temperature can increase by absorption of heat. The temperature can increase when you irradiate that particular body with the optical energy or light. If light is incident, then also its temperature can increase, or if you supply some heat, then also its temperature can increase. Now your sensor must measure if it is meant for the increase of temperature with the thermal energy supply, then whatever the optical energy is incident there, say from surrounding. So for that, what is the output that has to eliminate it? That means that comes the selectivity. If I want the temperature change due to a certain phenomena, it should select only that phenomena. Because of other phenomena, the output measurand may change, but it will not reflect there. That is the selectivity. So that means ability of a sensor to measure one measurand in the presence of others. Then comes the sensitivity. Sensitivity is a ratio of change in sensor output to the change in the value of the measurand. That is defined as the sensitivity. Okay, and speed of response is also an important parameter. That is time at which the output reaches 1 by E, which is 63% of its final value in response to a step change in measurand. That is the speed of response. How fast? Because in case of step change of the measurand, you need the sensor respond very fast, and its definition is the time required to reach 1 by E times, which is 63% of the output, desired output. So that is the speed of response. Okay. Now repeatability and stability are other parameters which you have to take into account when you are selecting or design a particular sensor. Repeatability means ability of a sensor to reproduce output readings under identical condition of the measurand. That is repeatability. Same conditions you are applying, the output of the sensor should be same. If it is not same, it is not repeatable. And repeatability may lose because of different problems in your design, different problems you are choosing of materials of the sensor, and different problems of your environment condition also. Okay. And the stability is another important aspect, and that is ability of a sensor to maintain its performance characteristics for a certain period of time. So that means how long your sensor is performing well, that is the stability. Okay. So with this I gave an introduction to the microsensors, and something I will continue on this topic in the next lecture also, and then I will discuss on the evolution of these MEMS sensors as well as market survey. Okay. Thank you. Let me stop here.